So the next talk is Evangelos, who's going to tell us about TT-bar deformations in any dimension.
Thank you very, very much. I'd like to also thank the organizers for letting me present here part of my work. So this is based on work that I did last year and the paper that we're writing now with Alexia, who's also here as a poster, not about TT-bar, but it's still fun. So I'd like to keep pushing on the propaganda we heard from Christian and Tsolakidis yesterday that says that stress tensor deformations have gravitational pull. This will turn out to be true. But let me start with an 8-page long motivation about why I do what I do. And the last 2 slides will be the results. So how do we deform quantum field theories? Great, the white you can see because I was scared that you might not be able to. So how do we deform quantum field theories? So that's the old way. You start from an undeformed or C theory, and you go to the deformed theory by just turning on a coupling and an operator. And then that's it, you're done. So then the question one may ask is that, is this all you can do? Or yes or no? Well, the easiest way to see that this is half of the story is to just take one derivative with respect to lambda here. You do that, and you end up here at the top. So people call this a flow equation, and they treat it as if something fell out of the sky, but this is what we were doing all along. It's just the simplest way of solving this equation. This equation is a principal of PDE, and it has only one initial condition, so it might be kind of sick. The initial condition is when you turn off the deformation parameter, you're supposed to go back to your undeformed theory. That's it. So you go on the left-hand side here, it's the left. So if your operator depends on your fields, and only on your fields, you can directly integrate out this equation, and you end up on this corner right there. That's what you know. However, there's another option. Maybe the operator depends implicitly on the deformation parameter. Then it's not that simple to integrate out this equation. Then the question is, what is the deformed theory in that case? Is it anything useful? Can we do anything about it? But also, what are these types of operators that depend implicitly on lambda? The only statistical data that I've given you here is just the undeformed theory, the deformed theory, the coupling, and the operator. So the only thing that implicitly depends on the deformation parameter is the deformation theory that I'm trying to find in the first place. So already this is a mess. How do you even answer this question? Okay. So already small overview. You give me your undeformed theory, you give me your operator, and I try to give you your deformed theory by solving the flow equation. Okay? The undeformed theory can be a CFT, interacting theory, or whatever you like to pick. What can the operator be? Well, let's consider the stress tensor. There is an arbitrary choice that I make here, but in principle, this type of thinking works for any other type of operators that has these properties. So the stress tensor for a minimally coupled theory is a functional of your deformed theory and its first derivative. So you see it fits very nicely in this family of operators. Oh, by the way, the operator can depend on the deformed theory or maybe derivatives of that, and the stress tensor is one choice, one consistent choice. Again, there are infinite choices you can make about an operator. You can build Lorentz scalars out of that, and go nuts. Who says that one is better than the other? Thankfully, we have a couple of Russian friends here giving us the answer. There is one special operator in D equals 2, classically and quantum mechanically, that one should consider, or at least should start from it. And that's TT-bar. People mention it, I think 3 or 4 times. We had 3 or 4 talks about this already. So what is TT-bar? It's just the determinant of this thing right here. And it's going to be important for later. Notice that the determinant in 2 dimensions, you can think of this as a matrix, it's just a quadratic polynomial in terms of the stress tensor. So D equals 2 quadratic. By the way, once you fix your operator here, you also fix its dimensions. So the dimensions of the coupling here is n to the minus 2, it's mass dimension. So this operator is irrelevant. So you're even deeper trouble because this is a principle non-normalizable. Okay. How do you solve the flow equation? There are many approaches to TT-bar. And it depends how strong you are, you can apply one or you can apply all of them. The standard way of solving it is just by, have it on the top here, just by guessing what the deformed theory should be. You can do that, you can just guess the deformed theory should be this. You plug it back to the flow equation, if you're lucky, you're done. However, the ansatz method is dependent on the seed theory you consider. And these deformations are notoriously known for being true for any type of seed theory. But we'd like to know the answer for any type of seed theory. We can also do perturbation theory, expand the small powers lambda, and then turn the crank, and you pick up terms. However, physicists, sadists, would like to have closed form results always. We actually prefer them. So there are other ways of attacking this problem, and these are in these 4 bubbles here. I have in the corners. So in the middle, we have our TT bar. We have our undeformed action. I shift to an action picture now because it's going to be convenient for me later. As I said, it's a power 2 polynomial. The scaling dimension and is -2. Okay, so one approach, by the way, these are just names. I'm not going to explain how each one of it works, but it's important to know that they're there and they're connected. One way is to couple your undeformed theory to a massive gravity type of theory, integrate out the auxiliary Vielbein. There are 2 Vielbeins in a massive gravity theory, necessarily, and then you're supposed to be done. That's your deformed theory. Again, I'm not going to show why it's true, but it's true. You have to believe me on that. Equivalently, there is another formalism deployed by Tsolakidis and friends, which says that instead, sorry, this is a ghost-free massive theory. There are no ghosts. That's what that is, and I'm going to use it in a bit. So equivalently, you can couple your undeformed theory to flat JT gravity, and that should also give you your deformed theory. There is also the change of coordinates that Masahito mentioned yesterday, and there is also random geometry formulation by Carty. Very well. As a second-order logical step, there are connections at radial cataphonography and in string theory, but I'm not going to talk about them at all. They're there, but these are second-order in terms of logical steps. These are the closest things you can do. So people, when they talk about approaches to TT-bar, they draw up stuff like this, and they say they're all connected like that, and then you should be able to get from one approach to another. However, if you sit down and you actually calculate, you will see that's not necessarily true. What is true is, yes, they're all connected. However, you can flow from the ghost-free massive gravity here, the top left corner, to all 3, but you cannot do the opposite from all 3. So this thing sits at the top. You can flow down, but you cannot flow up necessarily, or it's not that easy to flow up necessarily. On top of that, showing that using the massive gravity approach developed by Tolley, you can immediately show that the deformed theory is the correctly deformed theory in a very simple way. You just integrate something out, and you're done. So we're in D equals 2 here. So in D equals 2, it seems that the massive gravity seems to be the most direct, simple, and general method. This is true for any C theory. Okay, so if massive gravity is all that powerful, let's talk about it a little bit more in detail. So that's the answer for the deformed theory. You have your deformed theory there. You have your undeformed theory there. That leaves on E. That's a Vielbein. You have the massive gravity action here. This is addressing. You see lambda comes here in the denominator. Only this part is responsible for the deformation, the second part. So you take your S0, you couple it to that, you integrate out E, and that's it. That is if you can integrate out E. Okay, I'm just saying that if you do that, that's what it is. So because this part is responsible for the deformation, let me just take that and write it in a better language, because this is going to be convenient for me. If you define this Y matrix as the inverse of F times E, you can rewrite the dressing as a quadratic polynomial in terms of Y.
Sorry, in F, you minimally couple the original action to some.
Not necessarily. It can be anything you like. Not necessarily. Okay. So you use this parameterization here, and you see that this massive gravity potential there is a quadratic polynomial in terms of Y. And its particular limit of an arbitrary dressing G. On the bottom, where I again have my TT bar, which is again, as I said before, a quadratic polynomial in terms of T, which is a particular function, particular choice of a functional that is depends only on the trace of T and the trace of T squared. It turns out, if you look at this very closely for a long time, these two are directly connected by this simple equation. If you take one derivative with respect to lambda on this side, this equals on your operator. Notice on the left-hand side, you only have gravitational variables, so this is only gravity. And on the right-hand side, you only have field theory variables. So this is the operator you consider, stress tensor, powers of stress tensor. So this is inequality. I want to stress it. It's not a correspondence or anything like that. You have gravity equals field theory. There. Okay. So how does that work in higher D? In 2 dimensions, we had our gravitational dressing truncated as trace of the y to the 2 and trace of t to the power of 2. It would fluctuate there. However, in higher dimensions, this goes on, the implicit dependence goes on and on up to the power of y to the d. This is not a guess. You can derive actually that. And if you think about it a little bit more, this is a direct consequence of Cayley-Hamilton theorem about matrices, which says that if you have a matrix, you can only take the first d power of that matrix. You cannot go further down the road. Okay. This should be true in general for any deformation and for any gravitational theory I pick. Well, sorry, for any deformation, you can solve this equation and you get your G. And if you fix your G, you can find your F. You may try to fix both, but if this equation is not true, they're not compatible. Okay, so in 2 dimensions, we had that F was picked to be a polynomial of order 2. That's what semological says. So then in D dimensions, F will be picked to be a polynomial of order D. This is arbitrary, but it turns out that it works. The mass dimension of the operator now is minus D. It was minus 2, D equals 2. And now on the gravity side, in 2 dimensions, G was picked to be a polynomial of order 2 again in the Y. And then you pick in higher dimensions G to be a polynomial of order D. So you make these ansages for your F and your G. You see a polynomial of order D will have coefficients in front of each terms. So there is a lot of constants there to be determined. So you make these 2 choices. You plug them back in this equation. And you find that G and F are uniquely determined. There's only one solution. There's nothing else you can do. And why do you want to consider polynomials? Is because at the end of the day, you may want to thinking about quantizing your theory, and we only know how to quantize theories that have something to some power. If there are square roots and stuff, then we are in trouble. Okay, so how does the solutions look like? I feel like I'm going maybe too fast. I don't know. So on the gravity side, now we're in D dimensions. The gravity theory looks like this. Just the trace of y plus the determinant of y.
Sorry.
Yes.
Can you say a little bit more about that on the previous slide?
Yes.
So I've got 2 order 2 polynomials and one equation relating them, and you're saying that's enough to uniquely fix it?
Yeah, because they're polynomials. Then you apply the fundamental theory of calculus that says if you have 2 polynomials on 2 sides of the equations, the powers in front of the coefficient in front of the power of x to something will be the same on both sides.
I see. So you still have arbitrary coefficients in the polynomial.
Yeah, but they're all determined at the end by this equation.
I see. You're saying one side is determined inside of the other, but there's still a degree of freedom there in choosing. Yeah.
No. I'm saying that you make a polynomial ansatz here, you make a polynomial ansatz there.
Yeah. And that ansatz has to be 3 parameters.
Yes, and that has 3 parameters, but you fix them all exactly. Well, they're fixed at the end of the day. Okay. So the gravitational dressing in higher dimension answer looks like this. This is the only polynomial answer that I could find actually. So after a lot of soul searching, we were looking at this for almost a year now in order to find some connection to something. It turns out that this is a known thing by people that study ghost-free minimal massive gravities, and it was a theory that Hassan was one of the locals here, and Rosen came up in 2011. But that was only D equals 4. Similarly, there is a connection to a theory of gravity that Berkshire and friends came up in D equals 3. They called it topological massive gravity, but then they added terms to make it minimal massive gravity, and this contains exactly these terms. So you take, on the gravity side, you take your G, you have your S0, you take your G here as it is, you integrate out E, and you should have your deformed theory. That's it. Okay. On the field theory side, the situation is a bit more complicated. In D equals 2, the operator, you derive it to be this. That's TT bar. That's good. That's the first consistent check you can make. However, once you go in a dimension higher, you pick a quadratic part, but then you pick up lambda corrections that come with a third part of the stress tensor. And in 4 dimensions, you have again a quadratic part, a cubic part, that's the first lambda correction, but you also have a lambda squared correction, that's a quartic part. This particular pattern goes on and on. Thankfully for us, the quadratic part of each of these operators was also predicted as a higher dimensional analog of TT bar, completely via different independent method, via radial cutoff holography, but in higher dimensions. And these are the results. You can find them here.
Sorry.
Yes.
So you're saying that if you do this gravity analysis, you get the thing on the right part of the slide.
Yes.
And
This.
the
Yes.
parameter lambda is arbitrary.
Yes.
Is a new parameter.
No, lambda is a deformation parameter.
Okay, so there is
Lambda is a deformation parameter.
is the same that you would have for the TT bar for
It's-
the red part.
Yes, this lambda is exactly as the same, exactly like that lambda. Exactly the same. Yes. Okay, so this is the first small check that we're getting results that people derived previously, but we now have corrections as well on top of that. So one may stop there and claim victory, but there's all this big thing that needs to be filled out, but now in higher dimensions. So then we try to do that. What do we get? We start from here, and thankfully for us, as I said, it equals 2, this seems to be the thing that sits at the top. So everything else should come out as limits of this approximation, of this formulation. So we show that actually you can flow down to the random geometry framework, and you can understand this as a change of coordinates at some limit. Maybe the most important part, which we still don't understand, is what is this here at the right top? Because in d equals 2, this was flat 3D gravity, but this is a theory that's true on only 2 dimensions. So then what is this? We still don't know. On the corner there, I had string theory, but it only makes sense if you're a dimension higher. There is also a dimension higher in your world sheet and you're in your world volume. So is this connected to P-branes? This is still, we do not know. This is probably very interesting to observe. And this is what I mentioned in the last slide. This is where the cut of ADSD, CFTD, DS plus 1 CFTD part comes in. The operator that they predict is precisely the same as we have, quadratically, but we get the lambda corrections as well. Okay. I'm going to finish here. Hopefully, I've managed to convince you that stress tensor deformations are an interesting and modern type of research that one can do. And massive gravity provides a very natural framework for studying these types of deformation. So if you have a seed theory, essentially you want to deform that seed theory with F, that's a completely field theory statement. You can take that same seed theory and couple it to G, and that's it. So you see, this is where the duality builds up. You have gravity on one side, and you have field theory, definitely. So in D dimensions, we found a deformation that extends previous results. On the gravity side, we found also a well-studied gauge-free massive gravity, minimal massive gravity. And we partially recover other formulations successfully. And there is still a lot more work to be done to see if this really makes sense or not. If you have any idea, feel free to email me or bother me or even attack me. I like that actually, because that's how we make progress. But that's all I have to say. Thank you very much.
1 or 2 brief questions?
If I may. So when you have, can you go back to your slide with the result?
Here?
Here. Yeah. So on the left-hand side, you just have a deformed action, which is just a closed form result for the action, right?
For the dressing, not the full action.
Okay. And the right-hand side, is it the statement that the deformed action obeys a differential equation of the form d over d lambda of s lambda is equal to the right-hand side?
Exactly.
With that explicit lambda in it.
Exactly. Yes. That's exactly right.
So did you apply this to a collection of free bosons to see if
Yeah.
you can write this in closed form? Do you know?
Well, it's a huge mess. It's a huge mess. So for these checks, especially that check, we managed to confirm it with no kinetic term, just the potential term. Because the equations that you get are significantly more complicated as you flow in higher dimension. But it's an interesting problem. Actually, there are more you can do, but I don't want to spoil anything for now. Yes.
Final question.
Do you expect this flow in higher dimensions to preserve integrable models or preserve integrability?
I don't know. I have no idea. That's why I say there's a lot of things to do. So.
Okay, so let's thank Emmanuel for that.